Hello again. In this video, we're going to set up our Blackpill STM32F411 to communicate with our computer over the USB port. So we're going to start out by configuring the Blackpill to send the information that it's capturing into the buffer from the DMA or from the ADC and to send that to the computer. So how do we do that? Well, the first thing we have to do is come in here and we need to change the way the clocks are running. So we need to change this high-speed clock to use this ceramic or crystal resonator that's on the Blackpill, and both of these are present on the Blackpill. And then we need to enable our communications, which is this USB OTGFS, and we're going to put that in device only mode. And then we need to add the software for the USD device here to run it as a virtual comport. Okay. And you'd think that just checking that would leave everything in a good state, but we're getting a problem here in our clock configuration. So let's run the automatic solver and see if it can find a reasonable solution. And there we go. It found a solution where it runs our USB clock at 48 megahertz, which it has to be. But it set our system, our hardware clock down to 60 megahertz, which is not ideal. So let's change this. Let's try 96, which is, well, it's going to work. There we go. 100 megahertz will not work. We can just demonstrate that real quick. If we try and set that up to something that's not going to work, it runs the solver and it sits here and searches, and then it's going to come up and say, didn't find a solution. Can try other sources. Now it's getting fractional, and this might work, but I don't know what it's going to come up with. So yeah. See, it's got like fractional 90s in the camera. Just go back to what we had, which was nice and clean. So 96 megahertz, 48 on the USB clock, and it's happy. So great, we can generate code off of that. And that should run. And it does. So let's just take a look at the pulses coming out using our logic analyzer. And this is going to be less than 1 megahertz now, because we changed the system clock and we're calculating this based on what we think our system clock is. So it's now, this is at roughly 96, 961 kilohertz. So when we defined our timer 2, or timer 1 rather, which is generating that clock, we defined these user variables that we're using to calculate our clock. So in theory, all we need to do is update our HW clock from 100 megahertz to 96 megahertz. And generate code. And run. And we should be back to 1 megahertz on our ILX clock. There we go, back to 1 megahertz. Okay. And we haven't messed up our relationship between when we're starting the DMA and when we're sending the clock signal. So good. All right. I don't know why it opens up those random files every time when it runs. Okay, so we've got our clocks set up and our software as far as the USB setup. So now we have to go into our main file and do something with that. So when we use the USB, the HAL library that is set up to send data over the USB happily takes a pointer to a buffer or a block of data, but it doesn't want to send large amounts of data at once. I think you can get away with sending 4096 bytes in a block, maybe. I know that 2048 works. I'm not sure that I've tested the 4K block, but what we're going to do is just send it in smaller chunks. So we're going to send 512 bytes of data at once. So there we go. We've defined a USB block size as hex 200, which is 512 bytes. Okay, so how do we use that? Well, we're going to come down to our while loop down here, and underneath our capture and delay from waiting for the capture, we're going to do some USB sending, and I'm just going to copy this over from another file that I have. Paste that in. So what are we doing here? Okay. We've got to do some pointer arithmetic to make this all work. So to start off, we're going to define a little auxiliary variable as this is going to be the number of blocks that we have to send, of full blocks. So if we have an odd sized buffer that is not an integer number of blocks, this is going to give us the integer number of blocks just below our size of our buffer, so that we basically send a bunch of full blocks, and then at the end we're going to send whatever we have left over. So that calculates how many blocks we have to send, and that's based on our ADC buffer length, which is our ADC buffer is 16-bit chunks. So 2 times our buffer length is how many bytes, divided by the block size, which is 512 bytes, and that's how many blocks we have. Then we're going to go down here and start a for loop, and we're going to count from 0 up to our auxiliary variable. And then we're going to do a little pointer arithmetic here. We're going to say take the address of our buffer, treat it as an array, and we're going to use our index variable times our block size divided by 2 to account for the fact that we're in a buffer full of 16-bit chunks. And there we go. That gives us our index into our buffer, and then we're going to send our block size of bytes of data, and then we're going to wait for 5 milliseconds for that data to go out, and then we're going to go back and send the next block. And so we're going to send all of our full blocks, and then once we're done that, we're going to send our last bit of data. And the way we calculate that last bit of data is we use the modulo function here, or the remainder function rather. And so we're just dividing our buffer length by our block size, and our buffer length in bytes divided by our block size, and take the remainder of that. That's how many bytes we want to send, and the address is going to be the integer, the number of blocks times our block size. So there we go. Anyway, that's pointer arithmetic. I'm not going to explain it more deeply than that. That's a topic for programming tutorials, which this isn't really. All right, so that should work. We should be if we run this, we should be sending out blocks of data. And so let's compile this and run it. All right, it is running. So how are we going to check if this is actually sending data? I've got a terminal program here. I'm going to hook it up to the port for the STM32, which is this USB modem port. We're going to connect, and there we go. Every 500 milliseconds we're getting a crunch of data. So let's clear that, connect. There we go. We can view that. This is nice. We can view it as hex numbers, and there you see it's actually sending reasonable. The 14 or the 12-bit data, the high 3 bits are always going to be 0. So the most significant byte is going to be 0 something, 03 here in all of these ones. And then the least significant byte is going to vary. Anyway, so that's it. We're sending USB, or sending data over the USB back to the computer. That's pretty cool. All right. Now we need to set up to receive USB data. In other words, we want to be able to send commands to our Blackpill. So let's talk about how to send commands from the computer to the Blackpill. And while we're doing that, I'm going to talk a little bit about why I want to get this set up at this point. And the reason is shown in this monitor that's just spitting out data all the time. So right now this is is coming in every half a second because that's the way we set our code up. But when I initially figured all this stuff out, I was just sending the data as fast as I could pull it off of the ADC and send it over the USB. And this thing, the terminal at that point was just filling with crazy amounts of data, and it was really hard to figure out where one line started and the other one ended. So I ended up sending blocks of marker, basically a bunch of zeros, a bunch of ones in a pattern, like in a big noticeable pattern that I could pick up and search for to sort of mark the beginning of a line. And I implemented all of that, and then I noticed that it would work for a while, and then if you let it run for more than a few tens of seconds, there'd be periods where the data coming across would be all scrambled. And what was happening is the Blackpill was filling the USB buffer faster than I could read it off on my computer. And I'm like, this doesn't make any sense. I like could have changed the timing, and I thought about it, and I'm looking at the problem. I'm like, well, let's solve the right problem. So instead of just sending massive amounts of data from the Blackpill to the computer, let's have the computer tell the Blackpill, I'm ready for some data. And then when the computer asks for some data, send the computer data. And the rest of the time, when the computer is not asking for data, don't fill the USB bus with a bunch of crap. Because the other outcome is it was crashing the USB bus. I would start getting weird disconnects on my USB devices because there was just so much data, and it wasn't working right. So that's why we want to implement the ability to send commands from the computer to the Blackpill right now. In the future, once we get our ILX device and we want to control the exposure time, or the integration time is what it's called, of the CCD, so that we can manipulate that, we're also going to want to be able to do that from a command from the computer back to the Blackpill, which then will change the way that it's doing its timing pulses to control the integration time on the ILX chip. So we need to send commands from the computer to the Blackpill over the USB. So how do we set that up? Let's look at we don't need to change anything in our chip configuration. We've already got the USB working because we just saw it working. So the next thing we need to do is set up a buffer to receive data into. Now, the instructions that I'm following, or the way that I figured out how to do this, to give a nod to the person who put this out there, is this. I found this YouTube video by this person, Controllers Tech, that explained how to send and receive data to the PC using the USB COM port and a blue pill. And this is one of these machine narrated videos with good information, but it was just very hard to watch. And if you go to the website, the sheer number of pop-ups that come up off of this person's website are just, it's just incredible. So I'm not gonna go to the website because it's just painful. However, I did want to give a nod because that's where I'm getting this information from, and I have I have the website here. I've got the ads disabled right now. Like I've disconnected from the network so that the ads aren't popping up. And so this is what we're going to do. We need to use this CDC. Here in our code, we are using CDC transmit, and so it would make sense that to receive data we need CDC receive. Okay, so if you start looking for CDC receive, it's not a globally available function like this CDC transmit. You have to actually go to the file in our device hierarchy here. We'll just close this other stuff. Go to USB device and then app and then US CDC interface.c. And if we go there, we can find receive FS. And go take a look at that. So the predefined version of this function, it takes a buffer, a pointer to a byte buffer, and a pointer to or just an integer for the length of that buffer. That's discussed here in the code. It's a little hard to see because the comments are dimmed. So we're going to have to modify this somehow. And so the first thing we're going to do is go into our main and create ourselves a buffer of bytes. So here's where our ADC buffer is, and so we're going to go ahead and create a buffer of bytes. So, and this is going to be I suppose I should have marked this volatile too. Just for completeness. All right, we're going to create a 64 byte long buffer of bytes to use, and that's going to be our USB receive buff. Okay, so that's done. Save. Now we need to go back into this cdc if.c and set up to refer to that. And so the way we do that is up here in private variables, I think. Yep, private types. So we're going to declare an extern in the private types section. So I was in private variables. I think that's where we want it. Maybe not. Oh, it's down here. Private types. There we go. So literally would have been in the same spot, but we'll do it in the right place. So there we go. In private types, we declare an externally defined type to our of type buffer 60. Did I goon this up? Yeah, I did. In our main, we called this thing USB receive buffer. So we have to call it the same thing here. There we go. Now we're not being an idiot. Okay. Now we need to go down to the definition of this receive FS, and we need to do a little modification. And user code begin 6, user code end 6. So we're going to replace this with that. Anywhere here we need to change buffer to be our USB receive buffer. So what are we doing here? When we start out, when we get data, we're going to clear out the buffer that we had, the old data that we had, and then we're going to copy the new data that we received into our buffer, and then then we're going to clear out the buffer where that initial data was received and set it back to zeros. Otherwise, when the USB receive happens, it'll just overwrite that buffer with a terminating null as a string. So it puts a string into the buffer of what it got, and the old data may be there further down in the buffer. So we're just going to set it to zeros. All right, so we're clearing our receive buffer back in our main file, and then we copy the data that we received from the buffer that the internal receive function is using onto our receive buffer. We clear out the internal buffer, and then we return that we're done. Edit, indent. Source. Correct indentation, there we go. All right, so that should be good. Save that. Let's go back to our main. And now we need to do something with that data that is going to be being put into that receive buffer. So how are we going to do that? Well, we're going to check right here if we got the letter S as the first character of that buffer. So if the letter S is equal to the USB receive buffer 0, then we're going to do this stuff. Source, what was correct in Alt-I? There we go. Okay. So let's see if that works. So let's connect. Well, the first thing is good is we're not just getting mountains of data. Let's hit an S. Oh, there we go. There's a block of data, and it's continuously sending S. Well, it's progress. S. There's one block of data that should be clear data. Well, that's our 5,200 bytes of data right there. All right. So we have commands going from the computer to the Blackpill. So we're going to call it there. The next bit will be in a while when I'll show you how to use a little Python quickie to get the data off of the serial port and display it as a graph. So till then, bye.